In this video, we're going to discuss binary search trees, which are sometimes called just BSTs. So here's an example binary search tree. The key properties of a binary search tree are, first off, it's a binary tree, and you'll notice that no node has more than 2 children. And for any node, all of the nodes in the left subtree are less than the element stored at that root node. Every element in every node in the right subtree is greater than the element stored in the node. So here you can see that the root is 8, and every node in this subtree holds a value less than 8. It's in the left subtree, and all the values are less than 8. In the right subtree, we have these two values, 9 and 14, both of which are greater than 8. Now, one thing about binary search trees is, for a given set of values, there's no one correct binary search tree. Here's another tree, and in this case we have a degenerate tree, but you'll notice that even though the values are the same, it's still a binary search tree. Every value in the left subtree of the root is less than the root. Every value in the right subtree is greater than the root, and that holds for any subtree. So here, this subtree here, 9 is the root. There's nothing in the left subtree, and in the right subtree, all the values are greater than the value of the root. So let's suppose that we're searching for the number 5 in the binary search tree. We're going to start at 8. That's our root. And is 5 less than or greater than 8? Well, it's less than, so we're going to go to the left subtree. Now we're at 3. At 3, 5 is greater than 3, so we're going to go to the right subtree. Now we're here. 5 is greater than 4, so we're going to go to the right subtree again, and here we find what we're looking for. What if the tree doesn't have what we're looking for? So suppose we're searching for, let's say, 12. So we'll start at 8. We're going to go to the right because 12 is greater than 8. Here we have 9. We're going to go to the right because 12 is greater than 9. Here we have 14. So we're going to go to the left because it's smaller. But notice there's no 12 here. So that tells us that 12 doesn't exist in the tree. We don't have to keep looking, because if 12 was in the tree, it would be somewhere around here. Okay, so how do we create the binary tree? So here we have some numbers that we're going to add in this order: 9, 4, 8, 3, 2, 5, 14. So we start with the root, so that's going to be 9. Then 4 is less than 9, so it's going to go to the left. 8 is less than 9, so it's going to go to the left. There's a node there, 4. 8 is greater than 4, so we're going to go to the right. 3 is less than 9, and it's less than 4, so it'll go to the right of 4. 2 is less than 9, less than 4, less than 3, so it goes to the right of 3. 5 is less than 9, greater than 4, but less than 8, so it'll go to the left of 8. And 14 is greater than 9, so it'll go to the right. So here we have the same numbers, but in a different order. So now 3 will be our root. Then 14 is greater than 3, so it goes to the right. 5 is greater than 3, but less than 14, so it goes to the left of 14. 4 is greater than 3, less than 14, less than 5. 9 is greater than 3, less than 14, but greater than 5. 2 is less than 3, so it goes to the left of 3. And then finally, 8 is greater than 3, less than 14, greater than 5, and less than 9. 8 will go to the left of 9. So now that we've seen how to add nodes to a binary search tree, let's see how to remove them. So there's 3 different scenarios for a node that you might want to remove from a binary search tree. The first scenario is if the node has no children. In that case, it's very easy. So let's suppose that we want to get rid of 14 from our binary search tree. Well, in that case, we can simply delete it. So this is the one we're going to remove, and we're going to erase it. Now, suppose we have a node that has 1 child. So suppose we want to get rid of 4. Well, that becomes a little more difficult because it has a child. However, since it's just a single child, we can simply remove the 4. And now 5 will be the right child of the 3. The final case is, what do we do if a node has 2 children? Here, let's suppose we want to delete the 3. What we would do there is replace 3 with its in-order successor. Now in this case, if we did an in-order traversal, 5 would be the next node we found. But let's suppose that there was a 4 to the left of 5, then we would have to go to the node we're deleting's right subtree's leftmost node. And that node may have one child. It won't have two, because then it wouldn't be the in-order successor. But if it has one child, we can just delete that as well. So let's go ahead and erase that node. So we're going to delete 3, and then we'll move 5 to that value. And of course, in the way I'm drawing it, I'm erasing and moving stuff around. When you delete something in your Java code, you don't actually have to delete it. You just set that anything that's referencing to it to null.